And today I'm going to talk to you about the early decisions that we should be considering when designing a sustainable home. A lot of what I'm going to talk about is about operational energy, which isn't necessarily making a home sustainable, but I'll dig into that in a little bit more detail. I'll not really be talking about retrofit, but a lot of these things will apply, and hopefully we'll do a retrofit webinar at some point in the future. These are the main topics I'm going to cover. I won't dwell on that slide. I'm going to jump straight in and going to ask the question about what performance should we be aiming for with our new build, self-build homes. So we're aiming this at people who are building their own homes, although this could easily be for a developer as well. Do you want to build a home that's as bad as the law will allow? So this is an image of a thermal image from the inside of a newly completed home. This is in Scotland, and this has passed building regs, but we can see all that horrendous thermal bypass and air leakage into the dot and dab plasterboard behind that wall. I'm not going to go into all the technical detail of that today, but we should be pushing to design buildings that are much better than the law restricts us to. And is building regulations really good enough? And I would argue that it probably isn't. So a typical new build in the UK that obviously is meeting building regulations is achieving about 85 to 90 kilowatt hours per meter squared per year to reach about 20 degrees during the occupied hours of that building. So that's requiring those many kilowatt hours over the whole year per meter squared. So it's a fairly abstract number, but that means that for a 200 square meter house, you'd probably need about £850 per year for heating alone. We're not talking about hot water here. We're not talking about your other electricity demands, just space heating alone. But that's an as designed performance, and there is a real problem in the UK, especially with the performance gap. So taking that previous slide where we've got a building that should be performing in a certain way, but because the way that those materials have been compiled and put together on site, we are potentially seeing a performance gap of between 50 and 100% of the as designed aspiration and the as built performance. So instead of £850 a year, it could be £2,000 a year quite easily. And then we have at the other end of the scale a passive house new build, and this would cost £150 per year to heat for a similar scale of home for a 200 square meter house, because that only needs 15 kilowatt hours per meter squared per year. And then we have all these other standards, ENERFIT, the ENERFIT component method, and the ACB/LETI retrofit standards. These are all retrofit standards, so they're for existing buildings. So they haven't got the benefit of building things from scratch, and still these are achieving a fraction of the performance of a new build to building regs. So I would really argue that building regs is not the way to be building. So why passive house? Today isn't going to be exclusively passive house, but I think it is such a demonstrably good performance standard in terms of achieving what it sets out to achieve, and allowing a design methodology and a quality assurance process that achieves that it is the one to fall back on in terms of performance, comfort and health. So first of all, passive house buildings achieve an 80% as a minimum reduction in space heating requirements compared to a standard practice for a new UK new build. That's again typically in as designed, but as we can see in as built, it could be a lot worse. So that could be a much greater difference in performance. And passive house is an energy standard. So it has a maximum space heating and cooling demand of less than 15 kilowatt hours per metre square per year. So that's the total space heating or cooling over the year. So that's what gives that sort of heating bill number. But it also then looks at the heating or cooling load. So that's the amount of energy it requires to heat the building to 20 degrees C with an external temperature based on your local climate. And that design temperature will depend on where you are in the UK. The further south you go, the higher that gets. If you're up north near Inverness, like one of our listeners today, then this would be a lower temperature. So in Sheffield, it's minus 1.2 degrees C, and we would need no more than 10 watts per metre squared to heat when a house in Sheffield, when that external temperature is at minus 1.2. So that means, again, so our 200 square metre house would need a 2 kilowatt heating system. So that's the size of my wife's hairdryer or a typical fan heater that you can get from Argos. And then a maximum total primary energy demand of 120 kilowatt hours per metre square per year. So that's the amount of energy that's used for not only heating, but ventilation, cooking, showering, hot water, etc. All of those regulated loads that we have to run our homes. And then an air change rate, so the amount of air that leaks through the building fabric of no more than 0.6 air changes per hour at 50 pascals. So that's about 15 times better than building regulations. So what does that mean in reality? So 10 watts per square metre is about a tea light per square metre. So you could heat your home with a tea light per square metre. And then anecdotally, there was a guy, one of the first Passivhaus owners in the UK. He stockpiled incandescent light bulbs before they became impossible to get hold of, and put those into his light fittings in the winter when he needed that heat. And the extra 40 to 80 watts of excess heat per light fitting from those energy inefficient bulbs gave him enough space heating to heat his home to 20 degrees. But it's not just about energy, and I think in many ways this is often overlooked, and it's probably more important, or at least as important, is that none of the internal surfaces of any of the external building elements, and that includes windows, should reach any lower than 17 degrees C when the external temperature is at that target, that guide temperature, so minus 1.2 degrees C in Sheffield, and that we have good supply of ventilation, so that's 30 metres cubed per hour per person, or roughly on a typical house, that's about a new air change for the building, so a change of air, fresh air, every 3 hours roughly. And what does that mean? So that means that we are eliminating the conditions for condensation on the inside of the building. So those surface temperatures are high enough that we don't reach that dew point on the surface. So we no longer get condensation on the inside of our windows or condensation on other bits of our building fabric, which means that we don't get the conditions for mold growth and for things like dust mites, bed bugs, things like COVID-like viruses like high humidity or low humidity. So if we can get something that hits that sweet spot with our ventilation rates, then we can avoid the transmission of those as well. And then the big question, and this is kind of what this talk's all about really, is does Passivhaus performance cost more? And it shouldn't really cost significantly more than a building regulations new build. So typically the increases are around 5 to 10%. This is very different for retrofit. Retrofit is always an additional thing, so it's always going to cost more. But if you've got a new build and you make the early decisions we're going to talk about here in a reasonably conscious way, then that 5 to 10% should be very reasonable. It depends on these early decisions. You don't want to design yourself into a really high energy or really high cost corner too early. So this is from a Passivhaus costing document. But this QS is picking up the really important thing that if you add Passivhaus as a requirement later in your process, particularly after planning, then the only things you can really change are the things which cost lots to change, like better performing windows, more expensive solar shading, more expensive kit. Whereas if you start with the fundamentals, then they don't need to cost you any more. And then this these numbers that I've been talking about, these kilowatt hours per meter squared per year, they're based on our energy balance. So every home or every building has a series of losses on one side of our balance and a series of gains on the other. So our losses are through the walls, floor, roof, windows and doors. They're also through thermal bridges, so gaps in our insulation. They're through infiltration, so that's unwanted air leakage through the building fabric, and then they're also through ventilation, so opening windows or through a mechanical ventilation system of some kind. And then on the other side of the balance, we have our gains. So there are three components to that. Our internal gains, so those are the gains that come from us living in our homes, occupying them. They come from showering, from cooking, from running turning the kettle on, from breathing, and having your computer on, all those kinds of things add heat. We get some solar gains from the sun through our windows, and then the gap between the losses and the gains are our space heating demand. So that hand-drawn graph there is for an Enefit, so a Passivhaus retrofit, and that needs 25 kilowatt hours per meter squared per year. And then on right there is an early Passivhaus that we developed, and that has that 15 kilowatt hours per meter squared per year for its heating demand in that red part of the bar chart. So these are those sort of graphically drawn. So we've got our internal heat gains from light bulbs, occupation, we've got our solar gains, and then the only other thing that we can do is then top up those gains with heating. And then you can see that our losses are through the solid bits of building fabric, through the glazed bits, any thermal bridges, any infiltration or and ventilation losses. So we're going to talk mainly about fabric first, because this is where we get our biggest impact in a new build. And these are sort of the approaches that even if you're not developing a Passivhaus, you're just developing a reasonably comfortable home that you should be considering. So orientation, thinking about where the sun is. It's not always going to be a perfect orientation, but we should be understanding which direction we're pointing in and what benefit or not that gives us in terms of passive winter gain. But then we also have to think about passive solar gain in the summer and the fact that could give us overheating. So how do we manage that that overheating risk? We should think about the way that we organise our spaces, putting spaces that want to be warmer, get more sun towards the sun, and then those that maybe you want to be cooler, like bedrooms and bathrooms and things that could be put to the north or where we've got shaded parts of the site. We want to wrap the building in super insulation. We want to make it as airtight as possible so that we're minimising leakage. We definitely want natural ventilation. I'm going to talk a lot more about ventilation in a bit. We shouldn't be relying on natural ventilation for air quality, but we should have natural ventilation for purging, so for removing lots of excess heat in the summer. And it's still a really positive thing to be able to open windows in your home and in your rooms if you wish to sort of feel the open air, external air. Thermal mass is slightly less of an important thing as building performance has increased, but it's still worth considering whether you have sort of more mass on the outside of your building to reduce the amount of heat that gets in the summer, or maybe more mass on the inside of the building to even out those peaks and troughs in temperature, both in the winter and in the summer. And then obviously one lights for daylight. That makes a home feel better, more enjoyable to be in, but also means that we have to spend less on lighting. And why is Fabric First a good starting point? So these are passive strategies to improve thermal comfort and low carbon. They don't require any sort of energy input once they've been implemented. They're low tech, and they should help us deliver low energy demand. The ones I've just talked about are sort of primarily designed for a Northern European climate, although they have sort of their uses outside of that zone. And these principles are really sound and relevant. They shouldn't be sort of discarded just because we might want to step towards Passivhaus and we start to use bits of software that lead us down particular paths. There's still a load of benefit to following those rules of thumb. And we shouldn't be ignoring these basics. So if we don't understand and implement the basics of building fabric performance and getting those things right, then delivering that really low energy and sustainable home will be much more challenging. And with that challenge comes cost. It doesn't mean that we can't achieve it, but it will come at a greater cost. So to achieve Passivhaus in the UK, we typically require really high levels of insulation. And I'll talk about what decisions we make to influence that thickness of insulation. Extremely high performance windows, again, they can be variable within a sort of range depending on the other decisions that you've made, but they will still be really high performance. We need a really airtight building fabric, so we're aiming for 0 air leakage. And if we aim for 0, we'll get under that 0.6 air changes. We want to have a thermal bridge-free construction, not just to avoid any heat loss, but also to ensure that any bit of our building fabric doesn't get below that 17 degrees C number that gives us a risk for condensation. So condensation risk is a really big part of delivering a Passivhaus and making sure that you have a really comfortable and healthy home. And I'll go into mechanical ventilation later, but we will need a mechanical ventilation system with highly efficient heat recovery. Otherwise, if we're going to ventilate 30 meters cubed per person per hour, we're just going to lose too much heat through opening windows and things. So we'll talk about that in a bit. So we're on to geometry and form factor, and this is easily the biggest influence on performance and cost. It either means that you achieve a lesser performance for the same cost, or you achieve the same performance but a much greater cost if you don't pay attention to this. And designing a complex geometry will mean that no magical construction approach will make that building high performance and low cost. And I think that's really important. I think it's really easy as someone wanting their own new home to be built for them, to be designed for them, that you want the bells and the whistles and the sort of more complex design that demonstrates that you've got a self-build bespoke home. But as I'll show you, this can have really significant impact on performance and cost. So we're going to talk about form factor. So form factor is the ratio of usable floor area to building envelope. So if you have a form factor of 4, then that means you need 400 square meters of building envelope for a 100 square meter building. So the higher the number, the less efficient the building form, and also the higher number, the more expensive the build. So these are, again, we're keeping this 200 square meter house. If we have a form factor of 4.4, which we have designed homes with pretty much that form factor, then you need to wrap that space with 880 meters squared of building envelope. If we went to about as efficient a 200 square sort of detached house as we could, so form factor of 2.6, then that's going to reduce that thermal envelope area to 520 square meters. So if we're just thinking about the quantity of material that we need to buy to achieve the same performance, then obviously getting that number lower makes a really big difference, reducing the amount of thermal envelope that we need to build. And then if we're looking at Passivhaus or an equivalent level of performance, each one on that scale of sort of 0.7 here all the way to 4.4, each multiple of 1 on this equates to roughly 100 millimeters of air-filled insulation. So that's insulation like rock wool or mineral wool. Obviously, you can buy more thinner, higher performance insulations, but they're more expensive. So if we take our poor form factor, 4.4 form factor, so we need 880 metres squared of building envelope for our 200 square metre house and 440 millimetres of insulation in that envelope. If we reduce that to a 2.6 form factor, that area of building envelope drops to 520 and the thickness of insulation goes to 260 mil. So that makes a massive, massive difference. So we've multiplied those cost savings there. So these are some examples. So this is the first passive house we ever designed. And there are lots of reasons why it's a complex building. Although had we been more sort of cognizant of form factor at the time, it might have been slightly less complex. But still, this has a heat loss form factor of 4.3, which means it needs an average U value of 0.1, whereas building regs, the U values are sort of 0.15 to sort of 2-ish, depending on which bit of building envelope you're working with. This is still a complex building, but because it's 2 stories, the form factor gets quite a bit better to 3.3. And so our U value here is sort of 20% less good. So we're having to input less insulation. And then this is a house in Sheffield where we had a much tighter budget and had to design a building that was as compact a form as possible. So we've managed to get the heat loss form factor to 2.77, which means that our U values are even better again. I would also say, and we'll come on to this in a bit, but let's take this example. When you have a complex building, you also have a lot of junctions. And all those junctions are things that are more expensive to design. So they take more time. So you're paying your architect, your engineer, and perhaps other people more to design them. They're more expensive to build because they take longer. And they are higher risk. So every time you join materials together, you have a risk that something might fail, either straight after construction or during construction or some point in the future. And obviously, good designers will try and avoid those failures, but they are increased, the risk of. And so you've increased your cost in terms of envelope area, you've increased your cost in terms of insulation, and then you've increased your cost in terms of design and construction. So really worth bearing in mind. The next thing to do is to know your site, and your form factor and your site will go hand in hand, but thinking about what's inside and what's outside of your site boundary. So the things inside your site boundary, you tend to be able to influence. The things outside it, you can't. So they may have an impact on the performance of your building. So it might be that you might be overshadowed, or you might have some access issues. Or it might be that you can only bring certain materials onto site because of the access. So that will affect the way you choose what you choose to build your building out of. So you've got those sort of inside issues, and then you've got the outside your site boundary issues, which could be that there are trees, buildings, etc. outside your site that might overshadow you and you have no control over those. Or it might be that your proposal might be impacting on your neighbours. So you need to be very aware of that sort of two-way street in that regard. And also, whilst this isn't generally talking about performance, this is definitely talking about cost. And you really need to know, if you're building a new building, what's going on below the ground as well as above. Never have we had a client who has regretted paying sometimes quite a substantial sum for a site investigation to find out what they can achieve in terms of their foundations to get those as minimal as possible. So it really, really is important. And it's not unheard of to do site investigations before you buy a plot, let alone before you design your building. Think about orientation. So your site will have its ideal aspect. So this is a site for a house we've designed in Bramsbottom. We have a load of south-facing space, but our views are that view to the east. So we've ended up with a very east-facing building, which is absolutely fine and is the right decision to make on this site, but obviously is suboptimal in terms of passive solar gain, especially in terms of summer overheating. So it's something we then have to be very aware of as we develop the design for the building and develop the budget for the building as well. South does make the sun much easier. So this is that very complex bungalow, but we can see here that it has an almost perfect south-facing orientation and allows the low winter sun deep into the plan so that we get lots of solar gain, but then the high summer sun is shaded by the meter overhang that we've introduced above the windows. So that makes it really easy. East and west, south facing isn't critical, but east and west are much more difficult to deal with when it comes to summer overheating. They'll give you great winter solar gain still, but because especially in the west, the sun is still really hot, but it's low, have to think about movable shading rather than just fixed shading. So that's something that you should sort of budget in quite early because it can add quite a bit of cost, or think very carefully about the size of the windows, and obviously take advantage if you thick wall construction, even with your most compact buildings, we're going to have nice thick walls so we can enjoy those deep reveals and use those as part of our shading strategy. Glazing size matters, and this is just to bear in mind that glass is the best performing bit of any window. Windows are much worse performing than walls, but once you're putting windows in, whether you have a single large opening or multiple openings, it makes sense to think about the scale of these. So this is some output from an old PHPP, so Passivhaus planning package. All of the windows on that chart on the left have exactly the same performance, as in they're the same window, the same frame, the same glazing, but the different ratio of glazing to frame mean that our large window, 4.3 meters squared, has a U value of 0.72. So that's really fantastic for a window, really very good. When we move to our smallest windows, our 0.8 meter square window, that then has a U value of 1.01. So that is sort of nearly 50% worse than the bigger window, but actually it's the same product. So thinking about how you divide your windows up into bits will help you to achieve better performance for the same amount of glazing, essentially. And then full height windows, we love them. I mean, they're beautiful. And we have lots of homes where we've designed them with full height windows, but we have to do this with caution. So that lower portion, that lowest sort of 400 to 800 millimeters of a window, provides very minimal daylight to our space. It's only lighting that bit of floor next to the window, but it is giving us much more winter heat loss. So if we look back here, these numbers are actually from again, the complicated Passivhaus with an average U value of 0.1. But an average U value of 0.1, this window, the best window in the building, is still 7 times worse than that. So much greater winter heat loss. And then this is where we've got greater summer overheating. It's much more difficult to shade this down here, whereas a small overhang can shade quite a little bit of that window. So it has comfort issues, has energy issues, and it has cost issues. Glazing is much more expensive than wall. So whilst I've just said on one slide, do as bigger windows as possible, also do that with caution in terms of where you locate that window. Keep that above 40 centimeters, 80 centimeters above the floor, and that will make such a difference to your energy performance. Instead, think about framing views for delight. I think whilst blankets of glazing can look amazing, it's not very sort of discerning It's not sort of choosing a view and framing it, it is just giving you everything. Whereas I think sometimes moments like this window seat can give you absolutely fantastic appreciation of your view, give you plentiful daylight, good solar gain, but not give you loads of issues in the summer or the winter. And then those things to remember. So full height glazing is lovely, but it does introduce a greater overheating risk and more winter heat loss. Think about enough glazing for good daylight as being enough. So this graph here is the energy balance for, again, the complicated bungalow passive house. I'm going to go back to that slide. And you can see here that because we've shaded loads from above, and it's a south-facing window, we can actually have, you can see here, this 60, we can have lots and lots of passive solar gain and know that in the summer it's not going to cause us overheating issues. On almost any other building, that would be a really big warning to me that we were relying too much on solar gain, and we would need to think about how do we reduce the window opening area or increase the shading of that window so that we can minimize that risk of overheating in the summer. Yeah, so frame views for delight, and then don't over rely on glazing for that winter solar gain. Yeah, so I've said that. Just enough glazing for good daylight will almost always be enough for solar gain. And then going back to this sort of health side of things. So we've got our building surfaces that aren't cold enough to have condensation on them because they're really well insulated or have really high performance windows. But we also need to think about effective ventilation because that helps give us a healthy building and healthy people or healthy occupants. So why do we ventilate? So it's really important for our health. We need to change the air in our spaces so that we don't get build-up of VOCs, so volatile organic compounds that come off our furniture, out of our carpet, etc. They're not particularly great for us. Carbon dioxide build-up will make us feel drowsy and can make some people actually feel sick. And will also build up moisture, which will ultimately lead to condensation or to damage to our building fabric. So we need to really control this. Effective ventilation needs an air change of the house about every 3 hours. So if you were to do that with windows, you would need to open every window on your home for about 10 minutes every hour. So if you think about doing that in the winter, that would be a pretty miserable and uncomfortable winter, and you would lose lots of energy. So not only would you be quite cold, you would have to spend a lot more heating your home. You'd have to replace the heat in your home completely every 3 hours, which would be loads. And then also you can't really rely on the two energy sources that drive natural ventilation. So you can't rely on wind pointing in the right direction for at the right speed at the right time to give you your ventilation, and you can't rely on there being a sort of buoyancy effect that your warm air will rise and leave the building and pull in fresh air in the way that you need it to at every point in the year. So you're unlikely to ventilate properly if you rely on natural ventilation. So that's why we will almost always on a low energy building put in a piece of kit that uses energy. And that sounds daft, but when you see what energy it uses and then how much it saves, it makes a big difference. So MVHR will typically deliver about 0.3 air changes an hour, so an air change every 3 hours. And depending on the unit that you buy, it will give you something between 70 and 90% heat recovery. So 90% of the heat that would otherwise be lost through ventilation is being brought back into the home. The way that it works is that it takes all of the warm, moist, dirty air out of your wet spaces, your bathrooms, your kitchen, your utility room, passes that through a heat exchanger, and then fresh air coming into the building also passes through that heat exchanger, and it gets given the heat, but not the the other poor bits of the air, and it delivers that to your dry room, so your bedroom, your living room, your dining room, and therefore it's a balanced system. And typically it's centralized, so it's got a piece of kit and then it's ducted around the building. And this is a readout from my MVHR at home. It's fantastic when you see this, this idea that your outside air is 1.5 degrees, your supply air is 19.5 degrees, and the fan unit is using 30 watts. And that's the only energy that is using. So it's giving you that fantastic space heating benefit, because it's retaining 90% of that heat at the same time as ventilating properly, so keeping you healthy and keeping your building healthy. And yeah, your heating system then has very little work to do to top that up. So the benefits of MVHR, so relative humidity is kept in this ideal 40 to 60% zone. So I'm using some graphs that were produced by a friend who installed MVHR in her home in 2021. And you can see just in that first year of installation, she didn't do any other works to the home in that period. But you can see that the relative humidity was brought into that 40 to 60% ideal for much greater period. She had relative humidities coming up over 75% before, whereas once she brought the MVHR in, only very rarely did it peak above 60, and for very, very short periods of time. And then if we use, so this, she measured CO2 concentrations, and if you use that as a way of sort of identifying the air quality, both in terms of CO2 and VOCs, it's quite a good sort of proxy for that. Before MVHR, she was generally hovering around that sort of 700 to 800 parts per million mark, which is terrible for sort of drowsiness and alertness. And then once the MVHR was installed, then it was almost always below 600 or quite a bit lower, nearly to 400. So that means very much more alert and much better air quality. And then it also affects temperature as well. So not inputting any more energy into the house for heating, but even moving from just sort of fairly basic but window opening ventilation to not having to open those windows means that we're keeping the temperature in a much more comfortable 20 to 24 degree band, rather than sometimes getting as low as 15 degrees. Installing MVHR, as I say, it's a centralized unit, so you need to think about somewhere to put that quite early in the process, and then you need to think about your duct routing. But again, if you're designing this from scratch, these are really simple things to do, and shouldn't really impact on your sort of design flexibility. So up to this point, I've talked about sort of operational energy or operational carbon. So this is the bit that, as an industry, we've got much, much better at. This is the bit that us as a practice have concentrated on a lot for the last 15 years, but is only a part of the story. So if you think about embodied carbon and the carbon burps, so the initial carbon emissions of a project, if you were to start your project now, and in the period between now and then building it and starting to occupy it, you're going to create a huge amount of carbon, the embodied carbon in the building. And then if you've got a nice low energy, low operational carbon building, then the graph of during occupation is going to be very, very shallow. And then there's going to be another little burp at demolition. If we as a nation are going to achieve net zero carbon by 2050, most of the carbon in our building is not going to be in that operation. Whilst it's really important that we get the building really comfortable, low energy, and a healthy building, actually it's hugely important that we consider the embodied carbon, because that completely dwarfs the operational carbon. So going to go back to form factor, it comes into everything. So if we're building a more efficient form, we are using less material for the same square meterage. We don't necessarily have to build the biggest house in the world ever. I have a 130-ish square metre home. It's a 4-bed family house. It's brilliant. Sometimes I would like more space, but I don't really need it. And it's very easy when you've got a nice greenfield site and the opportunity to build something big, We don't necessarily have to do that. Obviously, it's all personal choice, but you're here because you're interested in this stuff. And if you want to build something sustainable, then I would say that building smaller and more efficiently is a very good way of doing that. And then we need to think about materials and their sort of global warming potential. This is quite a crude pyramid. It's a really useful website to go to and have a look at materials. But at one end of the scale, we've got aluminium sheet at 28,890 kilograms of CO2 equivalent per metre cubed. That's your global warming potential. And then right down at the bottom, we've got construction timber at minus 680, or wood fibre board. So kind of like a wood fibre insulation is down at minus 1,740. So we've got some really big differences between materials. Now, obviously, aluminium sheet, you might, if you were using it, even to clad your building, you're not actually going to need many cubic meters of that to complete your building. Whereas if you're building your building out of concrete, then you're probably going to need a lot of cubic meters of concrete. So it's not just the embodied carbon in the material itself, but also how much of it you use. And I would say that you should try and use as little of anything, including wood fibre insulation, because I don't actually believe in the negative numbers. I think at best it's zero. But we should use as little of anything we need to achieve our goals. So things like mass timber construction, CLT and things, I love it. It's beautiful stuff, but it will still use more carbon to build a cross-laminated timber building than it will do to build one that's using a lighter weight timber frame. So again, think about how much of something you really want to use. And now I'm going to go to things that are a bit less fabric and more about sort of systems and heating. So I'm going to just talk quickly about heat pumps. There is still, I don't really know why, there's still quite a lot of resistance to heat pumps in the UK. I have a feeling it's just the gas boiler lobby, but there's no reason why we can't use heat pumps on pretty much any home, existing or new in the UK, and we can see some really significant benefits. So if we look at a gas boiler for a 200 square metre house, this is a 200 square metre passive house, so it needs 3,000 kilowatt hours to heat it to 20 degrees for the year. So that means that for a gas boiler, and the gas boiler is normally about 90% efficient, we're going to need to pay only about £166 in gas per year, plus a standing charge we wouldn't otherwise need. So that's another 220 quid. And we're emitting to 750 kilograms of CO2 per year. That's the intensity of gas in terms of its CO2 emissions. Whereas if we take an air source heat pump, an average seasonal coefficient of performance is more like 4. And actually, we have now seen people that have achieved a SCOP of 5 from a heat pump over a full year period. So that's quite impressive. Would mean that we only need 750 kilowatt hours to heat our building over the year, because we only need a quarter of that energy. And okay, electricity is 22 pence per kilowatt hour rather than 5 pence per kilowatt hour. So our electricity bill is pretty much the same as the gas bill, but we haven't got to pay our gas standing charge, so there is a bit of a saving there. But the really big saving is that the CO2, it is a fraction. So instead of 750 kilograms per year, it's 121.5. So that's a really, really big saving. And I think worth it on its own. And also, our low energy building needs a much smaller heating system. So some of the issues with heat pumps are that bigger heat pumps do cost a lot more. They grow in cost much more quickly than a boiler does. But a lot of the costs that we hear about, these scary stories about £20,000 heat pump installations, are normally to do with upgrading the heating systems in an existing home. If you're building a new home, you've got a chance to do all that from scratch anyway, so it's not really an additional cost. But also a passive house or a really low energy building requires a really small heating system. So a 200 square metre passive house needs a 2 kilowatt heating system. So that is the size of your heating system, a single fan heater that you can buy from Argos. If you build your home to building regs, it's going to need probably 5 of those, but so a 10 kilowatt heating system. But that's if it performs exactly as designed, which we know it doesn't, or is less likely to. So that means that we've got, another 4 or 5 of these potentially that are actually needed to be installed to make sure that the building actually is comfortable when it gets really cold. So we've got reduced embodied carbon of our heating system. It's cheaper to buy, it's cheaper to run and service, and it needs less space. So all of those things mean that getting the building fabric right means that your servicing kit is cheaper as well. This actually came up on LinkedIn again this week. Wood-burning stoves. There's still a common sort of desire for people in their self-builds, and I do understand why. My parents have a wood-burning stove. I do love it, but they are not low carbon. Taking wood specifically for burning, which is essentially what we're doing now. We're very rarely using waste wood that has no other function. We are generally now producing wood specifically for the burning market, and they're not low carbon because that's not the most carbon efficient way of using timber. We want to lock that carbon in rather than burning it away. They're also pretty poor for indoor and outdoor air quality. So as soon as you open the door on that, no matter how good the piece of kit and how efficiently it's burning, is going to put particulates in your space, and it's definitely putting particulates into the outside atmosphere. And also they're overkill. It's very difficult to get a wood burning stove that is smaller than about 4 kilowatts. You can get really small ones that are designed for like canal boats and things, but then they're not really what people want to install in their homes, and they might be 2 or 3 kilowatts. But if you think that we only need 2 kilowatts to heat our whole house, if you put a 4 or 5 kilowatt one in your living room, you're going to cook. So yeah, they're not great. And you can see here, it's a bit fuzzy, but this is from the Air Quality Expert Group in 2017. Some wood burning stoves may have improved since then, but a wood burning stove would give out 3.1 grams per hour of particulate matter, whereas a diesel car, 0.17, or a modern HGV, 0.5. So huge difference. You could be running 6 HGVs and still put the same amount of particulate matter into the atmosphere as you do running a wood burning stove. If you really must have a living flame thing, which again, everybody likes that, think about a bioethanol stove instead. You can get them, they look so much like a wood burning stove. They can even have a fake flue, etc. So it looks completely authentic, but all it emits is heat and water vapor. So much, much healthier for you. And also they tend to be 1 or 2 kilowatts rather than 4 or 5. Do think about solar voltaics. The performance is increasing all the time. I'm sorry, I'm going to have to speed up a little bit. I'm aware I'm getting close to the end of our hour, and they're constantly reducing in cost. As I understand it now, if you talk to someone, say at Octopus Energy, they basically don't think there is a pitched roof location where they're not viable. Obviously, they're going to be less efficient on certain orientations and with certain shading, but they are viable pretty much everywhere. And there are now lots of in-roof options like this, where they look really slick rather than something that's sat on top of your roof. They are now a similar cost to lots of roof coverings, especially the more expensive roof coverings. So they are almost a like-for-like replacement in cost, and they will pay back on your investment. So they're really worth thinking about. And then batteries are really important. So We tend to have this sort of great generation in the middle of the day, but our power usage tends to be in the morning and in the evening when we're not generating power. So we're able to do that load shift where we are taking the energy that's generated, we're storing it for use when we're not generating as much. And that allows us to reduce our demand on the grid when the grid will otherwise be at under most strain. And then in the winter, when you're maybe not getting as much solar power, so I only get a kilowatt hour a day in the winter if I'm lucky at a house, I can still charge my batteries at night using a cheap nighttime tariff, and then I'm using that 7 pence a kilowatt hour electricity during the day rather than the 22 pence that I'd otherwise be spending. There's a question about being off grid. I'm not sure there are really great reasons to be off grid unless your site really is impossible to connect. I think having something that works with the grid is actually much more beneficial. So thinking about something like zero bills. So Octopus, they were talking about it being for 10 years, but all the data I can now find is for 5 years, but they will now guarantee homes with 5 years of zero bills. You need a certain amount of solar, you need a certain capacity of battery, and you need a heat pump and a smart meter, and then they will basically take electricity off you when you're not using it, charge your batteries when they've got excess, and so they will balance your use, make sure that you're comfortable and have the electricity that you need, but they will guarantee you no bills for a minimum of 5 years, which I think is pretty fantastic. Developments can range anything from 1 home to 500 homes or more. So it can literally, you can go to them and you can say, I would like to have a zero bills home, please. How do I go about this? I would want to be looking at it early enough in the process that you don't make a design decision that puts that in jeopardy. It doesn't actually have to have amazing fabric efficiency. They've done it with a 1980s house. So yeah. So I've rattled through that last bit, leaves me 5 minutes at the end for anybody if they have any questions. I'm going to stop sharing so that I can see if there are any. How was that? Sorry, that I felt like it was a bit of a rattle through in the end. Was that helpful? Does anybody have any questions?
Hi, sorry, can you hear me properly?
Yeah, I can hear you.
Hi, I'm Orshi. I'm joining you from Vienna. I'm still a student, but yeah, I'm a master's student over here, but I'm originally from Sheffield, so that's how I heard about you. Yeah, yeah, really insightful conversation. It was really interesting to hear about all of that. There's a lot of stuff that I did learn at uni, but it's nice to have that refreshed and also hear some new insights. My question is along the lines of embodied energy. You did touch on it briefly. Yeah. And I'm currently researching alternative materials in architecture, a lot to do with biopolymers and byproducts. I've recently looked into this material called ferroc, which is it's a blend of iron dust and silica, which is really strong. And I wanted to ask, in terms of striking that balance between obviously longevity of materials, which is not necessarily the case in alternative materials, and also that operational energy, do you have any input or opinion based on like alternative materials within passive house design?
I guess my position on this mainly, well, there's a couple of things. So generally our clients need to get a new build warranty. So they need to have something which has some level of industry testing. Because if they don't have that, then you're going to struggle to get a mortgage, which most people it's the way they fund their building. So that's the first step. The next thing is I'm not so worried about lifetime carbon. Is kind of you're hinting at there that let's take the kind of concrete timber frame thing, the argument. Well, timber frame may not last as long as concrete, but it should still last a very good length of time. We should still be expecting our timber frame buildings to at least last 100 years if they're built well. And okay, a concrete structure might last 1,000 years, but if we've not reduced the carbon burn in the next 5 to 10 years, what's the point? So I think it is really important that we do look at alternative low carbon materials, but they need to get through their testing processes really quickly if they're going to become something that can be adopted by self-builders who have to live, I guess, work in the real world and those constraints of mortgages and things and funding. If you haven't got any funding, if you don't need to get funding and you can just build your house outright and you're willing to experiment, I think that's amazing and exciting, but that isn't most people, unfortunately.
Thank you.
That's all right. Hi, Ben.
Hi. Cheers, Paul. That was ace. Really good. Thank you. Enjoyed it. I've got a question around space form factor and the ability to keep that rationalized for multiple dwellings across the site if you were building a few homes, whether there can ever be a kind of cookie cutter approach to passive house design for delivering it at scale.
I think there can be. It's obviously passive house. To actually get certification, you need to model each dwelling separately, and there will be shading conditions and orientation that will affect that, but there shouldn't be any reason why you can't take a very rational building form. You know, if you start with that premise of a rational building form and take some worst case scenarios in terms of orientation and shading to stress test that, there shouldn't be any reason why you can't take exactly the same product and spread and use it across a site. There is a timber frame manufacturer literally in this last week, or maybe even hasn't happened yet, and they're just announcing that it's about to happen, are launching a package of passive house design homes that you can then take and build. Now, obviously, those have to have enough scope in them to cope with changes in orientation and changes in shading, etc. And I haven't seen what they've done to do that, but there are definitely ways of doing that. And obviously, there's also the question about whether you do definitely need to certify. Certification is a great QA procedure, as much about your build quality as it is about the energy performance. So if you can get your QA procedures on site right and during design, then you're getting 90% or even more of the benefit of the passive house. And if some homes are 18 kilowatt hours rather than 15, is that really a major issue?
Yeah, just anecdotally on that point, sorry a contractor has built homes of the same type on the same site, some certified, some not, to achieve passive house, and they've definitely seen the performance gap increase on those where they've not carried out certification. So even if it's unconsciously, the gangs working on the dwellings that were going to be certified have done a better job than those that knew that they weren't going to be kind of it wasn't pass or fail for them.
That's really interesting, because you would expect that once you've got that embedded in the site, that they would have the same QA procedures, even if it's not the same performance. But yeah, obviously not.
Yeah. Thank you.
Any other questions before we wrap up? Thank you very much for joining us. I hope you found that really useful. Jacob will be sharing the slides, and hopefully, if it has worked, a recording from today with you shortly. Tomorrow, is it, Jacob, that you're going to be sending that out?
Yeah, I'll aim to do that tomorrow. Aim to send out the recording and the slides tomorrow. So, of course, yes, if anyone would like to discuss with us their low energy home, then we'll be really happy to do that.
Brilliant. Thanks very much, everybody.
Thanks, Paul.
Thank you all. Bye-bye.
See you.
Bye.
Thank you.